Welcome to the fifth and final of our July lectures in physics for 2015. My name's Professor David Jamieson. It's my pleasure to introduce tonight's speaker, Professor Anne Roberts. Anne has been a colleague of mine in the school for a very long time. She came to Melbourne originally after a Bachelor of Science and PhD from another university to the north of us, from a prominent harbour city in this nation. Yes, all right, it was Sydney. And then spent a tour of duty as a postdoctoral fellow in one of the leading universities of the United States, Cornell University, before returning to life in Australia and joining us here in the School of Physics at the University of Melbourne. Anne has had a distinguished career in all aspects of optical physics and photonics. She served most recently as the president of the Australian Optical Society, a tour of duty that finished, I think it was the end of last year. Not only in research, Anne has had a very influential career in supporting her fellow physicists, and indeed spent 6 years as the first female deputy head of the School of Physics in its more than 100-year history, under somewhat trying circumstances, I must say, but served that role with distinction and advanced the cause of our school in many ways in teaching and research. So presently she is the head of the optics research group here in the school, a thriving group with interests in many different fields. Those of you who are present a few weeks ago would have heard another member of that group, Professor Ken Crozier, speak on his research in the field of optical physics. So I know of no better person qualified to speak on the theme of this year's July Lectures in Physics program, the International Year of Optics. So please, International Year of Light, I should say. So please welcome Professor Anne Roberts. Anne.
So thank you, David, for the very kind introduction, and thank you all for coming out to help us celebrate the International Year of Light. As you can gather from David's introduction, my lifelong research passion is in the area of the physics of light. And so, you know, it is a joyful year for people like me to be able to share our enthusiasm with the broad public. And there's been a number of really excellent presentations in the July lectures this year. And one topic that that hasn't been discussed is the way that, or specifically is the way that light interacts with matter, the stuff that we see and interact with around us. And that's what I want to talk about tonight. So one of the key messages that I want to communicate this evening are, firstly, the fact that light does interact with materials in all sorts of ways. And that means that firstly we can use light as a very useful probe of those materials, whether they're cultural materials. So here we have some manuscripts, historic manuscripts, and these are priceless cultural materials that we want to be able to study, and we want to be able to do that in a non-destructive way. Similarly, we want to be able to study biological tissue and cells, and again, light gives us this incredible tool for being able to study these objects. And also, and I think Ken Crozier, for those of you that were at his lecture, would have talked about some of the interaction of light with nanoparticles, and I'll pick up on that again this evening. And the way light interacts with, for example, the stained glass in the beautiful Church of Sainte-Chapelle in Paris. Firstly, the interaction of light gives us a beautiful optical effect, but it's also telling us something about the material of which the stained glass is composed. So, and this leads me to what the second part of my talk will be, and that is the fact that we can use materials to control light. and we can control the various properties of light. And at the end of the presentation, I'll talk about the relatively new field of optical metamaterials and optical metasurfaces and the way that they are revolutionising optical technology. So I think all of the presenters in this series would have shown you a variation on this particular slide, which is highlighting the electromagnetic spectrum. And in the last couple of lectures, you would have been looking at the light and the universe and what light can teach us about the universe. But I'm showing this slide mainly just to highlight the fact that light is an electromagnetic wave. So when we talk about light, I like to think about light in its broadest possible sense. My career doing optical physics has spanned electromagnetic waves from microwaves, and I've even done some work in collaboration with people working with X-rays. So all of these are light. Light has an electric aspect and a magnetic aspect, and that's important when we think about optical metamaterials later on. The part of the spectrum to which our eye is sensitive and to which we respond is what obviously we call the visible part of the spectrum. But don't forget that we have the broad spectrum of electromagnetic radiation that will give us if we can do things in one part of the spectrum, often there are variations on that same application in other parts of the spectrum. So why is light such a fantastic vehicle for probing materials? Well, firstly, it has a number of different properties, and the way that that material will modify those properties tells us something about the material itself, and turning that around, we can use those properties or we can manipulate those properties of light with different kinds of materials. So firstly, if you look at the electromagnetic spectrum, we looked at the fact that light can be described as having a particular frequency or wavelength, or some sort of combination of wavelengths or frequencies, some sort of spectral composition. Light can also be polarised. I won't go into the details of that, but it relates to the direction of the electric field of the light wave. It can also have a defined direction, which can also be described in terms of the phase of the light. And also, and this is getting a little bit more complicated, we can also have light with varying degrees of temporal or spatial coherence. So light carries a lot of information. And by studying that information, we can infer things about objects with which it has interacted. Now, when we look at something with our eyes, and vision is a nice way of discussing how light interacts with objects, some of the objects are luminous. So you look at the lights in the room, light is travelling directly from those lights into your eyes, and they trigger the photoreceptors in your retina, which we perceive as vision. But if we have an object that's non-luminous, and I know you've seen the Lycurgus cup before in this, if you've been to some of the other lectures in this series, basically light can reflect from an object, and you will see those reflections. Also, light can be transmitted through the object, and again, you will perceive that particular visual effect. The colour can change, the light can be absorbed, the material could also change its polarisation, it could change its coherence, and also change the direction that the light's travelling in. So these sort of modifications all give us some insight into what's going on with the object of interest. So I just want to spend a little bit of time talking about colour. It's something that we can relate to. But in fact, there are an enormous range of ways that we can generate a change in the optical field that we will perceive as a colour. So for example, when light interacts with different atoms and molecules, that particular interaction will change its spectral composition, and we will perceive a different wavelength mix that we will see as colour. So this is, if you're looking at paint pigments, this is that kind of atomic process that you're looking at there. way a material, the geometry of a material also has a very key influence on the way we see colour. So this is a thin film of lacquer, and the colours that we see are related to the thickness of that film. So that's a geometric property. We also see the colours of the rainbow, and this is a consequence of a phenomenon called dispersion, where the optical properties of, in this case, the water, is a function of the wavelength or frequency, and the different colours are then, that are in sunlight are then dispersed or spread out. And I should say this photograph was taken in just last month. Of course, it's nearly the month before last, but this was last month, and I actually didn't take this photo because I would have been on a train going across Sydney Harbour Bridge at the time. It was a dark and stormy day, and my mother and I had just been to a gallery, and as we came out of the tunnel, suddenly there was this glorious late afternoon sun, and this absolutely magnificent rainbow was there. And then, of course, we pulled into Milson's Point Station, where everybody standing on the platforms got their smartphones pointed at the rainbow. So this actually set social media alight, this particular beautiful, beautiful rainbow. So dispersion can produce magnificent colour effects. And we also have a phenomenon called structural colour, and this is going to be quite important, particularly when I talk about the metamaterials later on in this lecture. If we look at the rings in a blue-ringed octopus, their colour is actually derived from basically a whole lot of different layers of different optical property materials. These are relatively thin layers, and they can produce this striking optical effect. And this has some relationship to the thin film colours I showed you before. And if you go and look at the colours of a butterfly, and if you sort of zoom in and move beyond doing optical microscopy into using electron microscopy, you will see that there is this amazing looking microscopic structure. And it's that microscopic structure that is producing some of the extraordinary colours that one sees in certain animals. We can also have diffractive effects, and again, for those of you that were at Ken's lecture, I think he talked about gratings, but if you look at a compact disc, you see colours that are being produced by the grating effect, and if you go and have a look at an atomic force microscope image of the surface of a compact disc, there are a series of pits that are producing that well, they're actually there to encode information, but those pits are what's producing the striking colour effects in the compact disc. So this is a grating from the Physics Museum here at the University of Melbourne. And if at any time you're passing through campus when the buildings are open, you can go in and have a look at the display cabinets in the building next door, and there's a lot of beautiful examples of relatively early optical instruments on display there. And this grating is about 100 years old. I think it's older than 100 years old. It was actually bought by Sir Thomas Labie, and he bought it because he wanted to undertake spectroscopy, because at the time that this grating was bought, this was the time when atomic science, the physics of atoms, was being investigated. So in order to remain at the forefront of contemporary research, it was very important to be able to undertake these kinds of investigations. So gratings were required. And this one was actually made by a very famous American physicist called Rowland, but the school actually eventually developed the capability of producing its own gratings, and the machines that were used to produce those gratings are on display in the museum as well. So again, we're seeing these striking colours due to artificial introductions of sub-wavelength or wavelength size features in a grating. And this results in very recent research coming from Singapore, and one of the people that did this research is a former PhD student of mine, Go Xiaoming. And what they have done is they've taken a painting by Monet, and I think it's called, let me just get the name here, it's called Impression Sunrise. And they've actually replicated it using a sort of particular arrangement of nanoparticles that they've used a particular fabrication process to do this. So they've created all these little nanoscale dots and arranged them appropriately, and these all have characteristic sizes and arrangements, and they have been able to control the colour quite precisely and produce a pretty good replica of this particular painting. But note that that black line there is 50 micrometres, and that is obviously a lot smaller than the original painting, I imagine. But you can see the fact that we can generate colours like this. And I should point out that there are groups in Denmark that are actually collaborating with car manufacturers to produce pigments using strategies such as this. And I'll just flip over to, I think I've got a camera here. And I'll show you some, these are some gold nanoparticles that have been lent to me by my colleague in the School of Chemistry, Professor Paul Mulvaney. And I may, is this, oh yeah, this is showing up quite well. And what these are suspensions of gold particles. Okay, so, and you can see here that gold doesn't look like the way you traditionally think gold would look. You can see, and these colours are related to the size of the gold nanoparticles. These are some more gold nanoparticles, and here the shape of, in each different suspension of these particles, the shape is slightly different. And this is producing a different colour. And again, it's just highlighting the fact that nanoscale materials actually have their own optical properties that are, to a large extent, independent of the material out of which they're made. That material does have an influence, but you can see that changing the geometry is significantly changing the colour that you're seeing. So we can use light to probe materials. We've just seen that there are a number of different ways that things can be coloured, and from that we can infer something about the material itself. So one of the most popular techniques for characterising objects is spectroscopy. There are a broad range of different spectroscopic techniques that can be used in different parts of the electromagnetic spectrum. There are also, if you actually image objects at different wavelengths, that gives you different information. You can also use the coherence of a laser beam to actually perform mechanical testing on objects. And there are methods for actually extracting the optical properties of different materials, and there are also phenomena such as fluorescence and photoluminescence that again can give you information about an object. So in order to take, if you want to perform spectroscopy, and I should say, you know, basically this is why this particular instrument was acquired. If you wanted to look at the spectrum that's produced by a particular light source, you could pass it through a prism and look at the spectrum that's produced, and depending on the light that you're using, you will see a different characteristic spectrum. We're interested in studying materials, and so if you have a light source here that you know what its spectrum looks like, it will illuminate a sample, and it has a certain spectrum here. It doesn't have to be flat like this, as long as you know what it is. It will then pass through a sample or be reflected from the sample, and that will actually change the spectrum. And that can then be detected. And a grating, for example, which actually can be designed to spread the light more than a prism can be used in this particular configuration. Again, light going through a sample, the grating creates the, will spread out the light, and then by moving a detector around or taking an image of it, it tells you something about the wavelength composition of the light that's passed through the material. And I've mentioned there are different types of spectroscopy corresponding to different parts of the electromagnetic spectrum. But one example of spectroscopy that I want to talk about involves studying cultural materials. And in particular, it's very useful to be able to identify certain molecular species in a particular artwork. And molecules have characteristic vibrations, and these can correspond to particular frequencies. their excitation. And so you can actually probe this vibration spectrum using infrared light or visible light and in the form of Raman spectroscopy. And what these methods do is provide a fingerprint of the molecules that are present. So for example, if you're interested in a manuscript such as this and you want to know what that pigment is, and you look at light passing through the pigment, you could end up with a characteristic spectrum like this, and you can compare it to a library of standard samples, and this will lead you to infer that this green here is indeed malachite. Raman spectroscopy provides similar information but enables you to do it using visible light. Visible light will excite both the electronic and vibrational states of a molecule, and the scattered light will have a slightly different wavelength, and that will give you some insight into the different vibrational states of that particular molecule. And this has been applied again to artwork, and so for example this particular painting here was thought to date from ancient Egypt, but an investigation of the blue pigment and the white pigment revealed them to be pigments that were produced long after this painting was thought to have been produced. So this clearly does not date from this particular period. I have a collaboration with the Centre for Cultural Materials Conservation, and one of the very interesting projects I've worked on with them was one involving a student, Liz Hind, who was investigating fluorescent paint. And one of the issues with fluorescent paint is it does degrade over time. So I'll just give you an example of, let me go to, let's put that over here. Here we have some examples of fluorescent paints here, and you can see these have been aged, and the aging I think goes up to about 80 museum years. Now Liz's PhD did not take 80 years, but there are ways you can come up with a total exposure that's equivalent to what it would receive in that amount of time in a museum. And you can see that the colours apparently here have faded over time. So the ones on the bottom line are the older ones. Another interesting aspect of this is that clearly it's fluorescent, so it can be excited with ultraviolet light. And I might need to, I will turn the lights off here, and you can see that you know, the fluorescence of the pigments is quite apparent, but obviously as things age, the nature of that excitation is going to change. So fluorescence is in fact one of the very interesting properties of a material that light can potentially excite, given the nature of the material itself. And over here, these are some samples that Liz studied, and this is just showing what they look like under, you know, conventional room lights, and this is under ultraviolet light. And again, after a period of time, the paints had degraded. And this is just a phenomenon. The pigments are fugitive, and that means the pigments fade over time. And this is one of the reasons I mentioned before the automotive industry has an interest in trying to come up with other ways of colouring things. You know, all pigments fade over time to some degree. These are particularly notable in this respect, but some of these metal-based types of pigments are less prone to that kind of aging. And you know, it's interesting thinking about, you know, the questions that the cultural conservators are interested in is, you know, how do they deal with conservation with these kind of pigments? How do they display the paintings? If they need treatment, how do they treatment? And there's a whole lot of very interesting questions that they need to address. Another area where the Centre for Cultural Materials has done some very interesting work is in the area of infrared reflectography. So this is using the infrared part of the electromagnetic spectrum. And this uses the fact that when you're looking at painting with visible light, which is what you normally do, visible light tends to be strongly scattered compared with infrared light. So infrared light will pass, will be scattered less than shorter wavelength light when it's passing through some kind of scattering material like paint actually is. And this is the reason when you put a torch behind your hand and you will see it looks red when it's passing through your tissue. It looks red because the red light is scattered less than the shorter wavelength blue light. So using this particular phenomenon, you can actually probe what is beneath the paint layer. You can actually see any kind of underlying characters or paintings that might have been there before. And there's some very famous examples where, very well-known painters have actually had an artwork and then they've just decided to paint over the top of it. So, I think these days you see things like that and you'd want to weep, but that's what they decided to do at the time. And it's also interesting to think about the way the artist went about composing the picture. So this painting is one of the most significant artworks in the University of Melbourne's collection. It's by William Strutt. It's called The Bushrangers 1852, and it describes an event that occurred on St Kilda Road near Elwood in 1852. Apparently this was very famous. It was a major scandal, and in the mid-19th century everyone was very worried about it. And this painting was painted I think a few years after Ned Kelly was hanged, and apparently bushrangers were very kind of interest again at the time that it was painted. But so you see this painting, it's very interesting, and if you actually look at this region over here in the infrared, you can actually just make out some shadowy figures here. These were originally painted by the artist who then subsequently decided to modify the composition. So for art historians, this provides really interesting insights into the methodology of the artist. And that's just looking at a painting with infrared light. You can actually look at artworks with a whole range of different wavelengths. There are cameras and detectors that work at in different wavelength bands. So for example, if you take an X-ray, that will give you insights into lead paints that absorb X-rays, and also maybe the structure of the painting itself. Ultraviolet light will potentially cause fluorescence depending on the nature of the painting, and can also highlight touch-ups and other issues to do with the varnish and the very top surface layer. And of course you can look at it with different colours in the visible part of the spectrum, and as I just mentioned, infrared light. And I should say multispectral imaging is not just used for cultural materials conservation, it's also used for studying other objects because it's incredibly useful. So I've used some examples here from cultural materials, but clearly a lot of these same techniques are equally applicable to studies in biology, earth sciences, and a whole range of other disciplines. So light is such an excellent probe of materials, and as I mentioned before, it is non-destructive, so it can be, if the light levels are low enough, it will have no impact on the objects being examined. It can be quite specific, so by using different wavelength regions, for example, you can be looking at different things. It can be very sensitive, and for those of you that went to Ken Crozier's talk, he talked about some very high sensitive sensing applications in using nanostructures. So light is very rich in information, as well as being very broadly applicable. So we can use light to probe materials, but given that materials do have this influence on light, we can actually use those materials to actually control light. And an obvious example is a colour filter. So, whatever it is in the Lycurgus cup, which is basically kind of nanoparticles embedded in glass, is acting as a colour filter. You can also use it to control energy flow. So a lens is actually changing the direction that the light is travelling in, and basically that's how they work. But if you're using some region of the electromagnetic spectrum where these filters don't exist, there are other strategies you can use. So for example, as part of my, actually this is when I was a research fellow at Cornell University, I actually made this thing here, but I actually studied it when theoretically when I was a PhD student, and the point of it was to act as the equivalent of a colour filter for microwaves, because the sorts of filtering techniques that are used with visible light just aren't available out there. And as a matter of interest, a few years ago I actually made a version of that that's thousands of times smaller. And so that's, you know, when I reflect on my career, the fact that you can do that is actually just extraordinary. The fact that we can make these nanostructures, which a nanometer being a billionth of a metre, it's just amazing. So this is an example where artificial materials can actually fill a hole that natural materials just can't provide. And similarly, we can come up with artificial materials that can actually control the flow of light to make lenses, for example, that are much, much smaller and lighter than a typical glass lens that's shown here. So one of the things that's gotten people very excited over the past decade or so has been the idea of cloaks of invisibility. So I'm going to talk about metamaterials, and you know, when people talk about metamaterials, often the next thing they think about is invisibility cloaks, and partly we have the media to thank for that. But can you use the fact that you control light? Can you make something invisible? Now, one way you can do this is to basically change the material itself so that light will just pass straight through the material without deviating, without being absorbed. And that was basically the strategy used by the Invisible Man in H.G. Wells' very famous novel. And to give you an example of how that might work, now I have to, that one, have I, okay. I've got a couple of demonstrations here. And, this is showing up the top there of that image, you can see some cotton wool, and I can refocus that. Yep, so you can quite clearly see that. And there is a liquid below it with a particular refractive index. And what we can do now is turn this over, and basically you can no longer see the cotton wool anymore, but you can actually see that there are some other objects in there that were actually embedded in the cotton wool that you couldn't see before. So what's happened here is that the cotton wool actually has the same refractive index as the liquid that's now sitting in, and that means that light is basically passing straight through it. And you might be able to see, I think there's a nail or something in there. You can clearly see there's an object in there that wasn't apparent when we were looking at it like this, because the light was basically reflecting off it, being absorbed by it in a way that meant that the light didn't go through it. I have another example here. This involves pouring liquids, so it could end badly. Okay, you can see that there is a beaker in another beaker. Oops. 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 Sorry about the slurping noise, yeah. So I've made it invisible. How good is that? So, and it hasn't involved any metamaterials or mysterious cloaks. Basically, it involves refractive index matching or impedance matching. So the light, there is no, because the way you see things is the light being reflected off that, that smaller beaker, and because we've cut down those reflections by matching it, we're not seeing that. If there is some sort of index mismatch, sometimes you can see little deviations in there, and it's difficult to see anything there, but sometimes little phase distortions can show up, and that actually is a nice way of doing what's called phase imaging, which is another interest of mine. Okay, so objects can be rendered intrinsically invisible. It means they have the same optical properties as whatever it is around them. So somewhat impractically, that's what the Invisible Man did. Just go back to here. Another strategy that people are looking at, and you might have seen this, this is kind of cute. This is an ad for Mercedes-Benz. And what they're trying to point out is that they're basically invisible. So I'll just, at the risk of incurring the wrath of Mercedes, I'll zoom through through this. But what they did as an example is to cover the car in LEDs. So one side of the car's got LEDs over it. And on the other side, they put a camera. And then they sent the image from the camera around to basically the screen made up of all of these LEDs, and then sort of went for a drive with this thing on. And you can see that basically you can see what's going on at the other side of the car. So this is an example of what we would call active cloaking. And obviously, I mean, I know it's an advertisement, but I get a distinct sense that the people looking at the thing going around are actually genuinely surprised and excited about all of this. So it is quite remarkable seeing that, even though you know exactly what they're doing. So let me just stop this. Come on, stop. Yep. Oh, hang on. And here's a recent one. Now, this isn't active cloaking. This is sort of a passive cloak, and you might have seen this. They've created this cloak, and then they've got an animal that likes getting inside things. If you want something to get inside something, you go for a cat. And they've made this sort of transparent box that's actually hiding the cat. They then made the mistake of going and getting a less cooperative animal. They put in a fish tank, and you can see the fish popping up there. You can't see the back half of the fish. Eventually they go and sort of prod the fish a bit, and you could see it coming out. I think there's a lot of the fish just sitting there. Yay. But so this is an invisibility cloak. Now this is not a metamaterial, but it does give you some ideas about the way people have been thinking about making cloaks. Hang on. And that is, they've got some prisms in here that they've created this region, and light is being steered around the outside of that region. So anything you put in there is not going to influence the light going around the outside. So here's Kitty over here sitting inside this particular box. Now this isn't what people are thinking about when they talk about metamaterials. This is kind of a, sort of chunky sort of thing that's using sort of traditional optical techniques to move light around. But it's using the same sort of ideas that have emerged from people's interest in metamaterials, and that is basically thinking about transforming space by using exotic materials to actually steer light around some sort of space, and things in that space are not going to influence what's going on outside and will basically be invisible. So this field is the field that people have, or a lot of the mathematics and the techniques that they've used to think about doing this is called transformation optics. And interestingly, it uses the same mathematics that Einstein used in the development of his general theory of relativity, which we're also celebrating the centenary of this year. Now the thing about it, if you want to do this, you have to be able to have materials that can have arbitrary optical properties, the sorts of material properties that nature just does not provide. And those materials actually have to vary throughout the region of that cloak. And they have to vary in a way that is really quite weird. And so if you want to do this, or even come approximately close to doing this, you need to be able to control both the electric and the magnetic properties of light. Remember, light's an electromagnetic wave. It's got electric and magnetic behaviour. So you need to change both of what we call the permeability, which describes magnetic response, and the permittivity, which describes electric response. And the sort of materials that people are talking about now are these metamaterials and metasurfaces. Another topic that has gotten people very excited, and again, people have kind of moved on a little bit from this, and that is the idea of coming up with materials with negative refraction. So clearly, if you've got that kind of control over the optical properties of materials, not only can you make a cloak, you can also bend light in weird ways. Now this animation here is showing conventional refraction. So we've got light going from, say, air into glass, and you can see the light is bent. This is a well-known physical phenomena. You can also see that the wavelength has changed as it's gone into this other material. So this is a material that's got a conventional positive refractive index. And there's a lot of interest in actually, it was driven largely by curiosity, in being able to create materials with a negative refractive index. And in fact, there was a guy called Veselago who in the, I think it was 1950s, actually came up with a whole theory of what would happen if materials could have a negative refractive index, and there's a lot of interesting things can happen there. But it was only in the last decade or so that people actually started practically implementing some of the ideas that he had. And if you've got a material with a negative refractive index, so up here, this is a model simulation I did. Up here you've got a positive refractive index, and down here you've got a negative refractive index. This looks very weird, okay? So the light is actually, it looks to you like the light down here is travelling upwards. The phase velocity is pointing upwards, but in fact the energy flow is shown by the arrow there. And you can see that the direction of the refraction is the opposite direction to what you would get from a positive refractive index material. So, you know, you can see why negative refraction has gotten people very interested, because this sort of thing is interesting to contemplate. And there's also the idea of the perfect lens. If you perform microscopy with a conventional lens, you have problems with diffraction that limit the size of the things that you can actually see. So there was a hope that if you had a negative refractive index material, light coming from point A will be negatively refracted at the first surface, and similarly at the second surface as it goes out into normal space, and a point here is mapped to a point here. So this is getting refraction and creating that perfect replication. One of the difficulties, however, is there are a number of practical issues. Not only do you need a metamaterial, but it actually needs to be very big to capture all of the waves that actually propagate out from this thing. So there have been some interesting demonstrations of this, but it hasn't progressed as far as I think people had originally envisaged. So how, in practice, would you go about making a material where you can control the optical properties? And so you need to go from thinking about conventional materials that have their properties derived from atoms to a material where the properties can be derived from the geometry. And if you think back to when I was talking about colour earlier on, we've seen that the geometry can influence light, and it can influence light in quite strongly. And what you want is some sort of structure that can have a negative permittivity, and in fact you can do that by having wires. You can also have a negative permittivity if you've just got a metal at optical and longer wavelengths. It tends to have a negative permittivity. But you also need a negative permeability if you want to create a negative refractive index material. And of course, if you want to be able to have an arbitrary refractive index or arbitrary permittivity and permeability, you need to have a similar sort of control. I'm just using the negative here as an example. And so you can create you can control the permeability by having loops of various kinds to control the magnetic behaviour. And the way these work is they're relying on resonances, and we know, I think I will put the camera on. This involves thinking, so that's document camera 2. I think I have to change cameras. Yeah. Okay, thinking about the idea of resonance, because these objects are electromagnetic resonators. And in the same way that a tuning fork is a mechanical resonator, and so it will produce a vibration at a typical characteristic frequency. We also have another mechanical resonator here, and I'll just creep around here. And so I can drive this object here, and I can turn it around and it will sort of move up and down in response to that. And then I can start turning this faster and faster, and eventually I will strike the resonance of this particular object here, and you can see that the amplitude becomes quite much larger than if I'm just moving it up and down. So you can see that. The other thing that can happen is that the phase, you can see it's now out of phase with the post that's driving it. And again, that's another characteristic of resonance, and in fact, it's one of the things that means that we can exploit the properties of these optical metamaterials to achieve arbitrary or a broad range of effective optical properties. Okay, so in 2003 there was this demonstration of, this was the first demonstration of negative refractive index. This is and this was done using microwaves. And so this structure, typical scale sizes of the order of millimetres here. And you can see this is just showing a unit cell, and you can see it's got these characteristic ring structures here as well as some straight wires. And this is just showing there's a requirement on the direction of the light is travelling and the direction of the electric and magnetic field there. But what this is a comparison of refraction by block of Teflon. Teflon is transparent at these frequencies. This is frequency up here, and this is the angle of refraction. And for a conventional material like Teflon, you can see that there is a refraction. It's at a positive angle, and it doesn't depend on frequency. But you can see that for the negative refractive index material, there is a negative refraction, but it is only occurring at over a very narrow range of frequencies, and that's because it's relying on this resonant phenomenon. Similarly, there have been demonstrations of cloaking, and this is one of the early ones. This was performed in, again, using microwaves. If you look at the scattering of microwaves by a copper ring, it looks something like this. If that region of space is now surrounded by a cloak, and it's clearly an imperfect cloak, but you can see that some of the, these wave fronts here are much flatter with this cloaked example here, and the amount of scattering has been significantly reduced. So doing these experiments at relatively long wavelengths is actually very challenging, and so trying to scale these experiments down to the visible part of the spectrum is something that is clearly a work in progress. And so there have been some demonstrations of cloaking at visible wavelengths using a sort of two-dimensional carpet type of cloak. You can put things over the top of something and hide it. And but the quest goes on to do these kinds of experiments. And what happens if you want to actually go down to doing things with visible light, you actually... I'm not sure I said that right. Yeah.
Yes, sir. Thank you, Professor. Thank you, Professor. You remind me there about the quantum, how we solve the problem, quantum light by method, because I have some two model, this model doesn't work. How we solve the problem by quantum light and matter?
So you're looking at the interaction of emitters and, say, metamaterials, for example? Or,
yes, dear.
Okay. Now, so classical models actually work quite well for a lot of the analysis that we're looking at. But did you come to Ken Crozier's talk?
Because we have two models. One Rebbe model, we call it the other one, but doesn't work. Only work for mathematics or model, not solve the problem.
Yeah, so look, it's an interesting area, and there are people undertaking research on it, and Ken is actually doing some really lovely work looking at really closely spaced nanoparticles and looking at tunnelling between them and some of those quantum effects. And again, we've reached a point where we can actually start to seriously think about studying those properties and investigating what the appropriate models are for predicting their behaviour.
Use it for technology.
Yeah, and potentially for technology, yeah.
Thank you, dear.
Okay, I'll take one final question. I think there was a question over here. Yes, sir, please.
My thunder, I was asking about the micro slits that bring the line in the 2Z experiment. And you've got slits crossing other slits. That must get awfully complicated and counterintuitive and all sorts of things from the diffraction pattern or whatever's going on through them.
Oh, look, you know, you can actually, there's a lot of flexibility. I mean, you're talking about things being complicated, but turning that around, it means that by tuning the nanostructures and the way they're spaced, you can produce all sorts of interesting effects. You can, I mean, you saw the example from the group in Singapore looking at, you know, replicating Monet's painting. That's a colour effect, but also there are examples looking at changing polarisation. You can, you know, you can manipulate, because light has all these properties, and with these structures you can actually change all of those properties. One of the issues is actually trying to change them independently of each other. So for example, if you want to make a lens, and we actually did some work a number of years ago making a lens, one of the issues was that not only was there's this variation in phase across the structure, but it was inevitably accompanied by a change in the transmission through the structure. So there's been some advances since then that actually kind of cleverly get around that to be able to change only one parameter at a time. But you're right, things are very complicated.
Okay, well, look, and thank you. Ladies and gentlemen, thank you very much for coming tonight. This brings the 2015 July lecture program to an end. Please keep your eyes open for the 2016 program. I look forward to welcoming you back in July next year. So thanks again for coming, and thank you, Anne.